have a look at this horrible problem. So we have to calculate electric flux through the open surface of the pot. Now the pot is shown in the figure, and effectively what we are asking is, if the pot is closed at all other sides, then this part is open. And if you put a charge Q at a distance L from this disk, what is the amount of flux? All right, so let's go ahead and try this problem. So you can pause the video and give a try. Okay, you don't have to use Gauss theorem or anything. You can just directly solve it. Now this problem is a little bit complicated. Okay, so what we are going to do is we are going to make this drawing in the following way. This is our disk for which we wanted to calculate the flux. We have a charge Q, right? So Q is at a certain separation from this disk. Okay, let's denote this separation as L, as said in the problem. And now you can clearly see the direction of electric field lines is radial, right? Is radial. So as compared to the previous cases that I discussed in the class, now this problem has got really horrible, because you can see the area vector of this disk is fixed. Okay, it's along x-axis. Okay, suppose it has some area, it has a radius r, then here we cannot directly calculate flux by calculating electric field and multiplying it. First, the magnitude of electric field at this point is different than at that point. And another thing is, electric field is radial. So you can see electric field at a distance has some magnitude, say E, but it is radial. Now, the area vector, on the other hand, has a normal in this direction. So corresponding to each field line at each spot on this surface, the area vector is changing. So we cannot solve it in simple way. However, if you look at the symmetry of this disk, right, it has a circular symmetry. So if I take this disk again, and if I make a ring, then you can see the area vector of this ring will have a fixed angle wherever you are on this ring. Okay, so using this symmetry, what we are going to do is we are going to solve this problem using calculus. So let's make our disk another time. We have to first make a beautiful drawing. We take a tiny radius, some radius r, okay, and then we make this ring. And now this ring is basically a little bit wide. Okay, now this width you will say is dr, right? Now this ring is located at a distance L from the charge. Right, if now we draw the electric field line, it's along this direction. It's this direction, right? And if we now take the area vector of this ring is along this direction. We will represent area vector like this. Now, if you see the symmetry, there is a fixed angle between them. Now, this angle, let's suppose, is theta. Okay? And the same angle is theta. All right. And corresponding to this dr, we can make small angle. Okay, after theta, we have to get theta. Okay. Now, let's try to calculate the tiny flux. Okay. Our tiny flux d phi is going to be E dot U. Right. look at E dot dA, what is the angle between E and dA? It is theta. So we can write it down. Is equal to E, we don't know the magnitude, dA of theta. All right. Now, the next thing is, we know L. So we can write some basic definitions from this geometry. So first thing is tan theta is equal to R by L. All right. Let us suppose this length from the charge Q to the edge of the ring is h. Okay. Now this h, we can write it down as h is equal to L sec. Right. Now, next thing is, what is the area of the disk, of the ring? This ring will have the area by R times dr. Very simple. Now we can use this relation tan theta is equal to R by L in the following manner. First thing is, we can write R is L tan theta, right? And then we can differentiate it dr so that we know it's L sec square theta times d theta. All right. Now the next thing we are going to do is, we are going to introduce these values. Okay. First, let's calculate everything. What will be the electric field at this point? Electric field at any point on this ring will be E is equal to Q by 4 pi epsilon naught times 1 by h square. All right. So now we have got all the relations necessary to do this horizontal calculation. Okay. I think after you follow my line of thought, you will be able to do it easily. Okay, so let's begin here. We can write our flux d phi is equal to E is Q by 4 pi epsilon naught times 1 by h square. H square is L square sec square theta. All right. Now, next thing is dA, so we can write 2 pi. Instead of R, we'll write L tan theta. Now, why I am doing this business is because I want to work in one variable. That variable will be theta. Okay, here you can see really there were two variables. One was R, because after R we took dr to define the disk, and corresponding to this we had theta and theta, the tiny angle. Okay, but we can integrate in one variable. So by using the basic relations, we can arrive to this. And now there is a little bit algebra. You can see dr we can write as L sec square theta d theta. L sec square theta. Right, and then there was a cos term remaining. So here we have cos. Okay, so now you have got this beautiful integral. You want to calculate the total flux. You have the total flux equal to this, and you are going to put an integral. Right, in order to define this disk, the smallest disk will be when theta is equal to 0. The smallest ring on this disk will be theta equal to 0. That will be the center. And then if we increase this angle theta up to an angle, say theta naught. Now what is theta naught? Theta naught is basically this angle. Okay. Now our theta naught is here. Okay. So you can see tan of theta naught is equal to r by m, right? So then we can span this entire disk. Now, if we rewrite this term, we have q by 4 pi epsilon naught, and then you have 2 pi. And a lot of terms will cancel. You see sec square, L square, right? And then tan theta into cos theta. This will become integral sine theta. Okay. Now, in this integral, what we are going to do, we are going to integrate between 0 to theta. Now, you can see this has become so simple. And if you rewrite it to epsilon naught by 2, you basically get minus cos theta. Okay, and theta changes from 0 to theta. All right, it's clear until here. Now, the next thing we are going to do is to put the limits of our total flux, phi total. Phi total is going to be 2 by 2 epsilon naught. It's going to be 1 minus cos. Okay, you can see this result is very important. This is exactly for the flux through a disk which is kept at a distance L and is of radius R. Right? And we know the relation. Here we have the cos theta, but this tan theta naught is R by M. Okay, so we can substitute and write from. Is this clear to you? Okay, so if this is clear to you, then our answer for the problem is q by 2 epsilon naught 1 minus cos theta. Okay, this is a JEE main and advanced level problem. Thanks a lot for your attention. Have a great day.